All right, folks, in this last video for this section for solving exponential equations, we're going to talk about how to solve for the rate of growth or decay. Now, we're going to do something a little weird in this one, and I'll tell you about it in just a little bit. It's not that weird. It's just your brain is going to want to reject it, but you just have to trust me that it's going to work out, okay? So here's what we have. We have a situation. We have a population of 400 bacteria that is growing continuously. After 10 hours, there are 10,000 bacteria, and we want to know at what rate is the population growing. So here, we're going to use our continuous growth formula, which is the Pert formula. So P times E to the power of R times T. Well, we have the starting value. The starting value is 400. And we know that we're going to put in an E. Now, it says at what rate is the population growing? This means that we do not know the percentage rate of growth. So we're just going to put an R there. Okay? Times, we do know how much time. It says after 10 hours. So we're going to put a 10 in for T. And instead of writing R times 10, we can actually, it'll be a little bit easier, or it'll look more familiar to us if we write 10R. So it's going to be 400 times e to the 10R power. And this is going to be equal to the ending value, which is 10,000 bacteria. So we're going to do a little bit of algebra on this to solve for R. Now, because the R is in the exponent, we know that we're going to want to use a logarithm to cancel the exponential base of e. But before we can do that, we have to get rid of this 400 that's in front of it. So we're going to divide by 400. Cancel, divide by 400. That's going to cancel some of these zeros, and we're going to have 100 over 4. 100 divided by 4 is 25. So we have e to the 10r power is equal to 25. Now, to cancel the exponential base of e, we just do a natural log. Do a natural log here and a natural log here. That'll cancel the e, and we have 10r is equal to the natural log of 25. And now, to solve for r, we just divide by 10 on both sides. And we have r is equal to the natural log of 25 over 10. So we'll grab a calculator, and we'll type in ln 25 divided by 10, and we get 0.32188. Okay, so r is equal to 0.32, let's say 19. And so we can now turn this into a percentage, and 0.3219 as a percentage is 32.19%. And then, because it's growing in hours, we would say that it's 32.19% per hour. Okay, so that is our rate, our percentage rate of growth. Let's try another one. All right, we got this other situation here. Now we have a population of 7,000 bacteria that are dying continuously. Okay, it says after 24 hours, there are 2,000 bacteria remaining. At what rate are the bacteria dying? Okay, so this is a continuous exponential decay, and so the formula for that is P times E to the negative RT. Now here's the weird part. Because we're solving for rate, okay, we actually don't have to put the negative on here. We actually can just use the Pert formula, P to the power of RT. Because what's going to happen is if we use the regular formula here, when we get our answer, it's going to say R is equal to negative. It'll have the negative in the answer, and then we can just remove the negative and go with the percentage. Now, if you feel better putting the negative on here, that's fine with me. I'm just showing you that when you're solving for rate, that you actually can just use the regular Pert formula again. Okay, so we're going to use this, and I'm going to show you how it's going to work out okay. So we're going to, our starting value, we have 7,000 bacteria times E to the power of R times, after 24 hours, R times 24. Now, like we did last time, instead of putting R times 24, we could just put 24R. So we put 24R is equal to 2,000 bacteria. Okay, now we can't cancel the exponential base until we get rid of the 7,000 that's in front of it. So the first thing we're going to do is we're going to divide by 7,000 on both sides. That's going to, we can cancel all the zeros here, and we have e to the 24r is equal to 2 over 7. Now 2 over 7, we're not going to reduce that. It's going to be a crazy decimal. We're just going to leave it as 2 over 7. Now, how do we cancel this exponential base of e? We're going to use a logarithm, log base e, which is just the natural log of e. So natural log will cancel. So we have 24r is equal to, and we got to do natural log to the other side. So over here we'll have the natural log of 2 over 7. And now we can divide by 24 on both sides, and r is equal to the natural log of 2 over 7 divided by 24. So I'll put that in the calculator. Natural log 2 divided by 7, close parenthesis, divided by 24. And I get nasty, here it is. R is equal to negative 0.0522. 0.0522. And so now the negative is on the rate. And here's what I'm showing you, is that the reason that happened was because I took the negative off of here. If we had used the negative on the r up here, there would have been a negative here, there would have been a negative here, we would have divided by negative 24, and our answer would have been positive 0.0522. So now here we just ignore the negative and we say that the rate is, if we turn this into a percentage, it'll be 5.22%. How frequently? Well, we put hours in here, so we're going to say per hour. Okay, and so that is our percentage decay rate. Okay. All right, here we have another situation. We got a situation where Arnold is investing $12,000 in a mutual fund. Now he wants to have $250,000 after 35 years. And what he wants to know is, what is the minimum rate of return for an account Now he wants to know, what is the minimum rate of return for an account that compounds monthly in order for him to meet his goal. Now, ignore this word minimum. That just means that that at a particular, when we solve for the rate, for the percentage rate, he wants to have that percentage rate or higher. But what we're really trying to find out is, what is the percentage rate in this formula? Now, this is a discrete growth model, but let's set it up as a discrete growth model, and I'm going to show you how there's actually a better way to do this than the traditional discrete growth model. So the starting value is 12,000. We know that it would be P times 1 plus the rate, which we do not know, over N. It says it's compounding monthly, so we'll put it over 12. To the power of 12 times, he wants to know, he wants to have 250,000 after 35 years. So we'll put a 35 here, is equal to 250,000. Okay? Now, what we would do is we divide 12,000 on both sides, but we would have a problem when we get here because we can't do log base 1 plus r over 12. We don't want to have a variable in the base of our logarithm. There's actually an easier way to do this than having a variable down here. Okay, so what you would really do is you would use a radical. We would wind up having 1 plus r over 12 to the power of 12 times 35. Well, that's 420. So actually, it's going to be really crazy. What we would actually have to do is we would have to do the 420th root in order to cancel this 420, leaving us with 1 plus r over 12, okay, is equal to 250 or 25 over 12. Okay, so you can try this if you want to, but I don't want to do it this way. This is not how I want to solve this. I want to show you that there's an easier way to approximate this rate. So we're not going to get the precise rate, but we're going to get a rate that's close. And here's what I'm going to show you. Did you know that in finance that you can actually use the Pert formula to approximate a rate? Okay, it's not going to be the precise rate, but just to approximate the rate. And we do a lot of approximating in business. Most of the time, or let's say most of the time, we don't have the precise number. We're guessing anyway. So why not use something close? And here's what I'm telling you is we use the Pert formula to solve for R in a continuous growth formula. But then when we did continuous decay, we ignored the negative and we used the Pert formula again. Well, here we are, we're doing a discrete growth problem, and we're still going to use the Pert formula. Here's what I'm trying to tell you, is that whenever you want to solve for the rate of growth or decay, the best way to do that, the easiest way to do that, is to use one formula, and that's the Pert formula. So let's do this. We're going to pretend that this is a continuous growth model. So we're going to put 12,000 in as the starting value, times E to the power of R times, it says 35 years. So instead of putting R times 35, we're going to put 35R is equal to, he wants to have 250,000. So we want to first divide by 12,000. All right, that's going to cancel some of the zeros. We're going to have 250 over 12. Oh, I messed that up before. I think I put 25 over 12. It's supposed to be 250 over 12, which can actually be reduced. If we divide by, let's say 2, it would be 125 over 6. That's right. Let's do 125 over 6. So we have e to the power of 35r is equal to 125 over 6. Now, we're going to do the natural log to cancel the exponential base of e. We're going to do natural log to both sides. That's going to cancel the e. And now we have 35r is equal to the natural log of 125 over 6. Lastly, we're going to divide by 35 on both sides. And now r is equal to the natural log of 125 over 6 divided by 35. So I'm going to grab a calculator. And I'm going to type in the natural log of 125 over 6, close, divided by 35. And what I get for r is 0.08676. Let's put 0.0868. So r is equal to 0.0868. And if we turn that into a percentage, move the decimal point over 2 places, we get 8.68%. This is approximately 8.68%. So basically, if Arnold invests $12,000 in a mutual fund at 8.68%, he should get about $250,000 after 35 years. Now, I want to prove this to you by putting in an R of 0.0868. 0.0868. So we're going to go ahead and do a discrete growth problem at 0.0868, and we're going to see if it comes out to $250,000. So we'll do 12,000 times 1 plus, the rate is 0.0868 over 12 to the power of 12 times 35. So 1 plus 0.0868 divided by 12 is equal to 1.00723. Okay, approximately. Let's put one more 3 on there. To the power of 12 times 35 is 420. I'll put a 12,000 up front. So we'll go $12,000 times 1.007233 to the power of 420, and I get $247,604.55. Now that's a little low. I know that that's less than $250,000, but remember, we approximated. So if you wanted to, instead of saying 8.68%, you can round up and maybe it would be 8.7%. And that's up to you. All we're doing is approximating here. But I want to show you that you can use the Pert formula for approximating the percentage rate in any problem. So anytime you are asked to identify a rate of return, the best thing for you to do is just use the Pert formula, no matter what kind of function it is, and then ignore any negatives and turn your decimal into a percentage, and you're good to go. That's all I have for you in this particular day. I'll have some work for you to do on all these different situations where we solve exponential equations, and I'll see you in class.